Hi there. My name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in the last few lectures of ECE3400 analog electronics, we've looked at diodes. I mostly talked about diodes as a route into discussing bipolar junction transistors, aka BJTs. So here I've drawn a typical symbol for an NPN transistor. So an NPN transistor has some N-type material on its collector and its emitter, and it has some P-type material in between. And that's pretty much all I'll say about the device physics of devices like this. We're mostly going to use the magic elves theory of transistors in this course. There's magic elves, and they conspire to make the currents flowing into and out of the transistor, and the voltages at its terminals satisfy various equations, and we'll take those equations and build some cool circuits. How those equations came to be, I'm not really going to worry about it here. If you are interested in the device physics, I recommend ECE3400, which is our course at Georgia Tech on semiconductor devices. So we do have two p-n junctions here, but this sadly will lead people to draw this incredibly misleading diagram. They'll draw a couple of diodes in a schematic that looks a little something like this. They'll put the base here, they'll put the collector here, they'll put the emitter here. And I see what they're trying to do. They're trying to indicate the junctions, but this is extremely misleading. It gives you the impression that you can build a transistor by just sticking two diodes together. That doesn't work. Now, in the active mode we're going to discuss, this diode junction here is forward biased, but the BC junction is in fact reverse biased. But even though it's reverse biased, you still get a massive current flowing through here. And this isn't a Zener kind of effect. This is a cool transistor thing that transistors do. So this is very misleading, and I prefer just not to draw things like this. So the arrow here has two different purposes. It indicates the direction of the p-n junction, thinking of that as a diode, and it also indicates the direction of current flow under ordinary operation. Now, we also have a p-n junction here, and despite what I just said, I am going to draw a little arrow here just temporarily. But again, you can't think about it as two diodes stuck together. This is a more complicated thing with more complicated behavior. So I am going to put a little arrow here just to indicate the direction of the p-n junction. So let's measure the voltage between the base and the emitter, the collector and the base, and the collector and the emitter. So I'm going to plot the voltage between the base and the emitter on the horizontal axis and between the collector and the base on the vertical axis. Now, this is typically the way people make a plot like this, but remember that the way that these p-n junctions are shown here, there's an opposite effect. So for positive VBE, this junction is forward biased, but for positive VCB, the junction here is reverse biased. Now, most of ECE3400 analog electronics is going to take place in what we call the active region. So that's this upper right corner where the BE junction is forward biased, but the CB junction is reverse biased. And notice in the active mode, the voltage at the collector is bigger than the voltage at the base, which is bigger than the voltage at the emitter. And in this class, we'll generally bias our transistors to have that property to operate in this region. Now, if both of the junctions are forward biased, then we say that the transistor is operating in the saturation mode. Now, if both of the junctions are reverse biased, then we say that we're in the cutoff mode. So digital logic systems typically operate by switching between these cutoff and saturation modes. So that would include your classic 74 series transistor logic, TTL logic, although that kind of logic family has largely gone out of style and has been replaced by CMOS logic. Now, if the BE junction is reverse biased, but the BC junction is forward biased, then we say that we're in the reverse active mode. This is not a standard operating mode for the transistor. There may be some strange special applications that I don't know about that use this mode on purpose. If so, please leave a comment below because I would be interested to know about that. But generally, operating in this mode runs the risk of potentially damaging the transistor. In the reverse active mode, the current is flowing from the emitter to the collector, and that's just unnatural. Okay, so that was all about NPN transistors. What about PNP transistors? Basically, what you do is you take all of the current arrows and reverse their direction, and you take all of the voltage measurements and reverse the direction of those. So VCB becomes VBC, VBE becomes VEB, and we wind up with a slide that looks something like this. So now we have current flowing out of the collector and out of the base and into the emitter, and we've flipped around the directions that we're measuring the voltages, and our PN junctions are now facing this direction. Now, the way this is usually drawn, we don't have the emitter down here. We actually flip this upside down and put the emitter at the top and the collector down here at the bottom, because that's the way this will most often show up in a schematic. I think that's enough for now, and in the next lecture we'll look at the equations that govern the behavior of BJTs in the active mode.